And welcome back, everybody. So, in the last video, we talked about the minimization principle, talking about how we could set up our minimization problems in a multivariable setting, and specifically with regards to quadratic functions, and how we might be able to figure out when there are minimizers to these quadratic functions, and when they might be unique global minimizers. So, with that information, we're going to start applying this to various settings, and the first on our list is addressing one of the questions in the motivating video, talking about what kinds of problems we can solve with minimization problems from the linear algebra standpoint. And one of them was the closest point problem, right? So to set the stage a little bit, we would like to answer the question of which points on the line y equals 2 plus 3x, in fact, which point, not points, which one is closest to the origin. And we look at this and say, okay, I can draw a line between these guys and say that has a particular distance to the origin. This one has a particular distance, but that one is shorter than this guy. And if we go too far, we make the line too long again. And it looks like there's something in the middle here that is going to make sure that we have definitely have the smallest size, the smallest distance on this line that is has smallest distance away from the origin. So at least on in the geometric sense, it looks like this problem does have a solution, and we're going to go ahead and start figuring out. Oh, geez, my app just crashed. We're going to start figuring out how we might go about solving this guy. How we might figure out which points, or how do we know that I found the correct point here? And this is the part that kills me. I want to be able to get rid of these little points here. But when the app crashes, I don't have an undo. Oh, shoot. Let's see if I can zoom in a little bit here. Meh. Close. We're getting close, guys. We can do this. Come on. If you're at home, cheer me on. Hey, there we go. All right. So back out to page width. There we go. Back out to draw. Kill off that. Phew. Okay, and we want to find the point on the line that is closest to the origin, and it looks like we do get it. And if we were doing this in Calc 1, the way that we did this before was we would look at the square distance function, right? We would actually literally go to this function and ask, when is this smallest, if I can go ahead and use y equals 2 plus 3x and substitute that in, which is exactly what this guy is down here, d of x by y of x. And that turns out to be 10x squared plus 12x plus 4. I can differentiate that, set the derivative to the 0, and find that x should be a minus 3/5, which seems to agree with the picture up here that this might be around minus 0.6. Right, that the x coordinate there would be about minus 0.6. And that seems reasonable. And, well, that's because calculus works. So, indeed, we are able to use calculus to figure this out. But, so not only do I get that, but I can also tell you what the closest distance is, right? If I plug in x equals minus 3/5 to y equals 2 plus 3x, then I will get 1/5 for y, and again, that seems reasonable. Now, the distance then would be the square root of this d function, right? This is the square distance function, so I need to take the square root of whatever my solution is for d. So this distance is exactly the square root of 2/5. All right, so that being the case, that is what calculus can do for us. But if we zoom in a little bit here, we are minimizing a norm, right? So what we can see just threw a kind of a symmetry argument that if I go too far if I go too far above or below a certain location on this line, then I'm going to be increasing the distance rather than decreasing it as I move along the line. Now, these lines are going to make angles with the original y equals. I should label that the original y equals 3x line, and this is an x-axis. There we go. Right. If I look close enough here, this is a very particular line that we have in mind. That this line that separates growing solutions from the minimizing solution is that it's perpendicular to the line that I'm restricted to. Right, and this actually isn't too hard to see. If I think about blowing up a circle around this, I'm asking for all the points that are a certain distance away from the origin. If I blow that up just enough, that circle is going to be tangent to this line, which means that it's going to be perpendicular to this radius here. So sure, that makes sense that we should expect there to be some orthogonality coming into play. And what orthogonality is going to do is allow us to skip over the calculus, right? So the only thing standing between us and a solution would be the calculus in a higher dimension, right? And this is the stuff that we're trying to avoid, that multivariable calculus. What we can do instead is pass through orthogonality, and that will get us to a solution all the same. So we're using the fact that orthogonality produces minimization results, and this is exactly what calculus set out to do in the first place as well. That we're trying to solve a minimization problem, but in this case, we're doing it in a very particular context. So this is first and foremost an orthogonality problem. So let's see what our work says about reframing this as such an orthogonality problem. So specifically, we have a new problem statement now. So let W be a subspace of a Euclidean inner product space, not necessarily the standard one, but an inner product space on our M. All right. And we are given a point that is not on this subset necessarily. It might be, but it's more interesting to think about the case where it's not. Then we would like to find the points that minimize the distance with respect to this norm. And remember, this is the square root of W minus B inner product with itself. Right, so this is the norm induced by the inner product. And we're trying to minimize that distance over all points, all vectors in that subspace W. And our first observation is that minimizing D squared, right, the square distance, is going to do the same exact thing as trying to minimize just that norm, just the original distance. And this goes back to this problem in calculus, where we really don't like dealing with square roots, so instead we just square everything up. And it turns out that, sure, this will find the same minimizers, right? Minimizing D squared is the same thing as minimizing D, or it'll produce the same minimizers. And go back here, all right? So that's all this is saying, is that we would like to, instead of minimizing D, minimize this function in the box. And by using the fact that this is equal to W minus B, inner product W minus B, we can simplify it to this red box, putting everything in terms of the inner product itself. So we'd really like to minimize this square distance term, and that's where the focus should be. Cool. And second observation is that if we were given a basis for this subspace W, doesn't matter what kind of basis, just a basis, then we could write any W within that subspace as a linear combination of these basis vectors Wi, and then going off of our work from chapter 4, then sure, we can do all this work in terms of these inner products of the W vectors with themselves, right? So we're taking the problem about vectors and turning it into a problem about or a statement about their coordinates. So just like we were constructing our Gram matrices before, we get exactly the same setup from that. That this square norm W is exactly an inner product weighted by some Gram matrix, however you'd like to pronounce it. So this K matrix is the Gram matrix of this basis beta with respect to not just any old inner product, but it's got to be the dot product here. Or is that right? No, it's related through this K matrix, so it's a weighted inner product. So technically, what we would have here should be a weighted matrix. There we go. And then these xi's would be the coordinates of the beta coordinates of this W vector from above. So we can take a problem about vectors and turn it into coordinates, or a question about coordinates, and that's all I'm saying here. So, third observation. So in a similar fashion, so we can take care of if I go back here, we can take care of this W squared term. This B squared term is fixed, so we can just kind of play with, let him be whatever. We don't only have to compute that guy once. We don't have to vary B. It is a constant. So the norm squared of W term is taken care of by this observation in number 2. And we're going to take care of this W inner product B term in a similar fashion. We're going to turn this into a question about coordinates so that we wind up with twice inner product B being equal to some combination of these terms of the basis vectors Wi against B. Right? We seem to be getting somewhere. So if we go ahead and set F equal to all these inner products, much in the same way that we set our K matrix based on a Gram matrix, then we're slowly building the problem from the previous section, where the last thing we have to do is set the B, or set our constant C equal to the square norm of the vector B. And we have now produced an optimization problem for this quadratic function. And we're doing this, we're doing two things when this happens. First, we are taking a question about the closest point problem and framing it as an optimization of some quadratic function. And two, because we're taking questions about vectors and turning them into a question about coordinates, this is the really important piece here, is that this problem is allowed to take place in an totally abstract inner product space, and it actually puts the problem right back into some Rn. And specifically, I think we are allowed to go ahead and use the standard Euclidean inner product. Yeah, we have to, so I'm going to go back and change this. Whoop. So we shouldn't be getting rid of this guy. It is based on the standard inner product space, because we're using this dot product up here in our quadratic form. So specifically, we are definitely back in the standard Euclidean inner product space. But in particular, we've taken a question about an abstract inner product space and put it into Rn, a standard Euclidean inner product space. And this creates the following theorem statement. That because we can do this, we can go ahead and apply this really as a corollary to our minimization principle. And specifically, if we have a basis, right, if we choose coordinates for this subspace W in the abstract inner product space, then given any vector in the total inner product space, the points in W, so W star, the point that is closest to the vector B with respect to the norm induced by the inner product, is unique, right? It exists first and foremost. There is a solution. That solution is unique, and I can tell you exactly what the coordinates are for this guy. This x star, these are going to be the coordinates of w star in this beta basis. All right? And it's exactly the k inverse times f that we had from the previous video, where k is the Gram matrix for beta, and f is going to be the collection of coordinates of it's the collection of coordinates for b with respect to beta. So I should write that down. F equals the beta coordinates of b. Right. So we're just taking everything from before, for everything in the Euclidean setup, and trying to adapt the abstract setting so that it has Euclidean coordinates. And the distance then of this solution is given exactly as c minus f times x star. So in this case, it's exactly what we had before. Right, just setting up k, f, and c to be very specific values. Right, to see this guy in action, let's go to the next page. So from before, our motivating example, talking about how we can find this guy. So this is y equals 2 plus 3x, right? How we can find the point that is closest to the origin along the dashed line. We can go ahead and translate this guy to the origin so that w is a subspace, or we can actually just translate the entire problem. So move the axes down or up, as it were, so that these guys are in the same relative position to one another, but so that w is now a subspace rather than an affine space. All right, so that means that we have the following setup, where I would like to find the points on V that are closest to the vector B, right? And W is going to be that subspace spanned by the vector 1, 3. And B is going to be how I had to shift the origin down along the y-axis. Okay, so that would mean that this vector here, 1 by 3, would correspond to W1 as part of my beta basis. So all I have to do here, I actually wind up with a really simple problem. My Gram matrix has exactly one entry in it, and my beta coordinates for f have exactly one coordinate in them. And I see that the problem now turns to trying to minimize this d squared function, or this d function, which is the square norm. And this turns out to just be 10x squared minus 12x plus 4, which is exactly the same function that we had before when we were talking about this from a calculus perspective. And we can check that x squared equals k inverse times f, right? K inverse, right? The inverse of a 1 by 1 matrix is just the 1 by 1 matrix that flips that entry over. So k inverse is literally the number 1/10, and f is the value minus 6. So we wind up with minus 3/5 for our critical point, which is exactly what we got before. Then w is going to be like the w star, the point on this line that minimizes this guy should be somewhere over here, which means that I want this vector to be w star. Okay, so if I go ahead and plug in x star equals minus 1/3, I multiply that as the weight that goes onto this the beta basis. Right, I'm trying to translate this back into a vector on w. And the thing I wind up with, and keep going, kill things, there we go. Then multiplying this minus 3/5 times the vector 1 by 3 gets me this vector. Okay, so this is exactly the vector down here that I was drawing. That this is the guy that should be W star. But notice how W star was actually translated a little bit. So what I have to do is add back what I took away at the beginning of the problem. So actually goes up a little higher than that. Come on now. There we go. Should go up right about here. And you'll see there's the 90-degree angle that I make with the original affine space. So this is exactly the minus 3/5 by 1/5. If I add back, or subtract off, shall we say, the translation by b, then I'm adding negative 3/5 by minus 9/5, and I'm adding to it 0 by 2, and there's the minus 3/5 by 1/5 that we had before from calculus. So orthogonality is, in one sense, replacing the minimization problem. It's saying that we can use orthogonality to guarantee that we have a minimizer. And we're going to go ahead and kill the video here, because the next thing we're going to talk about is how we might frame this in terms of projections. So we'll see that perspective next time, and we'll talk a little bit about how we'll have, this is a good jumping off point for other subjects, right? This is applied linear algebra after all. So we'll have a little bit of a discussion about what you can do with these outside of linear algebra.